see this question. In the following C function, let n greater than m, of course integers. It's Euclid GCD algorithm. Okay, this is one of the standard algorithm. So it is this procedure also called Euclid GCD algorithm. So what is time complexity to find greatest common divisor of two integers n greater than equal to m? Greatest common divisor of two integers n greater than equal to m. Okay, so just best case if you think of it, say if n modulus of m if 0, if n modulus of m is 0, GCD of nm is become m. Okay, under assumption m is smaller or equal to n. So otherwise the n modulus of m is become n. Okay, so this m is become, the smaller number become first parameter, and this n modulus of m value is become second parameter, like we do recursive call. So for example, so n is 125 and m is 30. We need to find greatest common divisor of 125 and 30. So the algorithm works like this. Okay, GCD of bigger number is first parameter and the smaller number is second parameter. So 125 modulus of 30 is not 0. 125 modulus of 30 is not 0, it not returns. Now it calls the one more function. Okay, then the second parameter is become first parameter, GCD of 30, and now second parameter is become 125 mod 30. 125 mod 30, okay, is 5, right? 125 mod 30 is 5. Now, so GCD of 30 comma 5. GCD of 30 comma 5 and 30 modulus of 5 is 0. 30 modulus of 5 is 0. So then it returns 5. Okay. So GCD of these two numbers. Okay. GCD of 125 comma 30 is 5. Like this it compute the Euclid GCD. It is one of the fastest algorithm, fastest computer algorithm which can run in the computer. So to compute the GCD of two numbers, right? Okay. So now best case of the algorithm. Okay. Best case time complexity of the algorithm. By chance m is divisible of n. So let's say n equal to 125. And m is 25. If m is divisible of n, then directly one function call only executes. Okay, GCD of 125 comma 25. Okay, so it computes n modulus of m. N modulus of m is 0, so that directly it returns m. Okay, so 125 modulus of 25 is 0. Then the first function call itself, it returns 25. Okay, so best case time complexity of this Euclid GCD algorithm is constant. Okay, best case time complexity of this algorithm is order of 1 if m is divisible of n. Okay, so let us see worst case time complexity of this Euclid GCD algorithm. Okay, worst case time complexity of the Euclid GCD algorithm. So the Euclid GCD algorithm required more recursive calls. Okay, this Euclid GCD algorithm required more recursive calls if n and m are two consecutive Fibonacci numbers. Okay, worst case time complexity. Let us see what is that worst case time complexity. So this Euclid GCD algorithm behaves worst case. this about GCD algorithm. So behaves worst case if n are consecutive Fibonacci numbers. Consecutive Fibonacci numbers. We'll back to this analysis. So let's consider some Fibonacci terms. Okay, the Fibonacci series is 1 1, okay, 2 3, so 5 8, okay, 13 21 and 34 and 45. Let's say you wanted to find GCD of these two numbers. Okay, this is some Fibonacci series. Assume we feeded input to the algorithm is two consecutive Fibonacci numbers. Then it required more number of function calls. Then this Euclid GCD algorithm takes the more number of function calls. Let us see this one. So we call GCD of, so first parameter is 45, which is bigger number, and second parameter is 34, it is smaller number. You need GCD of these two numbers. Okay, so here n is 45, okay, so m is 34. Okay, these two are two consecutive Fibonacci numbers. This kind of numbers, if we given as input to the Euclid GCD algorithm, then this algorithm takes more number of recursive calls. Let us see why it takes more number of recursive calls. Okay, see, there is a unique behavior for the Fibonacci series. Okay, the Fibonacci series, the next element, the previous element is, okay, slightly more than half of the next element. Okay, so 34 is slightly bigger than half of the 45. 13, 21, slightly more than, little more than half of the 34. Okay, 13 is little bigger than half of 24, and 8 is little bigger than half of 13. Okay, 5 is little bigger than half of n by 2, means half of the 8. Okay, 3 is slightly bigger than half of the 2, means the next element is, okay, not like next element, let's say previous element. Previous element is slightly bigger than half of the next element. Okay, so let us see what happened here. So n is 45 and m is 34, two consecutive numbers. Okay, then 45 modulus of 34. Okay, we compute 45 modulus of 34. Okay, is not 0, right? So 45 modulus of 34 we compute in the function. 45 modulus of 34 equal to, so 21. Okay, so it's not 0. It's not 0 means one more function is called. So next function call, for next function call, this 34 become first parameter. This 34 become first parameter. This n mod m is become second parameter. This n mod m is become second parameter. Look the algorithm once. Okay, if n modulus of m is not 0, if n modulus of m is not 0, this m is become first parameter. The second parameter m, smaller number m, is become first parameter. N modulus of m is computing, that is becomes the second parameter. Okay, so the no need means simply you can replace this n is the second value, n is, so n modulus of m. This m is become first parameter, the second parameter n is become n modulus of m. Okay, so similarly here, so this 34, the n modulus of m is not 0, 21. This 34 become first parameter, this n modulus of m becomes second parameter. Again compute n mod m. Okay, 34 modulus of 21. 34 modulus of 21 is become 13, not 0. Not 0 means again it calls the function. Again it calls function. It is becomes GCD of, this 21 is become first parameter, and 34 modulus of 21, 13 is become second parameter. Third function call is made. Okay, see previous two inputs. Okay, after one function call, this 125 modulus of 30 reduces drastically. Okay, so 125 modulus of 30 is become 5. Okay, so the value is reduces drastically. Okay, so then that much reduction is not happening here. If you observe 45 modulus of 34 going to 21 only, not so small. 34 modulus of 21 is going to 13 only. Okay, so compared to 125 reduced to 5, but here 45 reduced to 21. Okay, similarly here 125 modulus of 25 directly becomes 0. Okay, but here 45 modulus of 34 is 21, 34 modulus of 21 is 13. Okay, so the n modulus of m is becoming close to n by 2. It's close to n by 2. Okay, so let me explain a few more function calls. Okay, then so here 21 modulus of 13. Okay, 21 modulus of 13 is 8. Okay, still not 0. Again it calls one more function. This is become GCD of 13 comma, the second parameter become first parameter. 21 modulus of 13 is 8 is become second parameter. Now it's a fourth function call. Okay, so again it computes 13 modulus of 8. 13 modulus of 8 is 5. Okay, then it's still not 0. So again it calls the function. It becomes GCD of 8 is become first parameter. 13 modulus of 8, which is 5, is become second parameter. So in this function again it computes 8 modulus of 5, n modulus of m. 8 modulus of 5 is 3, still not 0. Okay, then again it calls the function. It becomes GCD of the 5 becomes the second parameter, and 8 mod 5, 3 is becomes first parameter. 5 becomes first parameter, 8 mod 5 becomes second parameter. Again it computes 5 mod 3. Okay, 5 modulus of 3 is 2. See, the n modulus of m reduction is very less compared to the previous inputs. That's why it takes the more number of iterations. Okay, so still it is not 0. Means again calls the one more function. It calls GCD of 3 is become, okay, so first parameter 5 mod 3 is become second parameter. Okay, so again it computes 3 mod 2. Okay, 3 mod 2 is become 1. Still it is not 0. So again it calls one more function. It becomes GCD of 2 is become first parameter, 3 mod 2, okay, 1 is become second parameter. Now, so it computes 2 mod 1, okay, 2 modulus of 1 is 0. So because n modulus of m is becomes 0, then it returns m. Okay, finally it returns 1. Okay, so then see, if n is 45, m is 34, if two consecutive Fibonacci numbers, n is 45 and m is 34, if two consecutive Fibonacci numbers, okay, so many function calls are made. This is the worst case scenario for the Euclid GCD algorithm. Okay, so here you can understand one thing. If n and m are two consecutive numbers, n and m are two consecutive Fibonacci numbers, okay, n modulus of m is close to slightly bigger than okay, n by 2. Okay, bigger than n by 2 na. So 45 modulus of 34 is slightly bigger than half of 45. Okay, n modulus of m is close to, okay, this value is close to n by 2. Not too smaller than compared to n by 2, almost close to n by 2. Okay, so closest value of the n by 2. But by chance, if n and m are not consecutive numbers, n modulus of m is become too small compared to the n by 2. Okay, so n modulus of m is slightly bigger than n by 2. Okay, So that means this n is first parameter. This n is first parameter. We computed n modulus of m. N modulus of m is becoming close, not exactly equal, close to n by 2. So then see 45 reduces to, n is 45. 45 reduces to half of them. But 45 is become first parameter after 2 calls. Means after 2 calls, n reduces n by 2. Okay, so because the second call m reduces. Okay, first call n reduces to n by 2, second call m reduces to m by 2. Okay, so assume this is m. Okay, according to the input, this is m, not 34 is m. M modulus of 24 is becoming close to m by 2. Okay, then this 21 n is become half, close to half. Okay, 21 modulus of 13 is 8. Okay, n becomes n by 2 square. Okay, but this 8 is become first parameter after 2 calls. Okay, after 2 calls, this n is become n by 2 square. Okay, then after 2 calls, okay, this n is become n by 2 cube. Okay, after every subsequent call, n is become n by 2 power k. So once n is 2 power k is reaches to 1, then it will terminate. Okay, these number of function calls are log n. Okay, close to log n. Okay, k is the number of function call, are close to log n. So other function calls are m reduction. Okay, so this m is 34, right? M is become close to m by 2 after 2 calls. Okay, m is become close to m by 2 after 2 calls. And 13 is, see, the 34 mod 21 is become 13. The 13 become first parameter now. 13 modulus of 8 become 5 is after 2 calls. Okay, so m is become m by 2 square after 2 calls. Then up to so on. Then m by 2 power k is should be reached to close to 1. It is log m calls, log m base 2 calls. Okay, so the total depth of recursion are number of function calls. Okay, total depth of recursion or number of function calls are so close to log n base 2 function calls plus log m base 2 function calls. Okay, log n base 2 function calls plus log m base 2 function calls. But we know that n is greater than equal to m. Okay, n is 2 consecutive numbers. Okay, n greater than equal to m. If n greater than equal to m, then log n is become leading term. Okay, log n is become leading term. This cost is become order of log n. Okay, this is the worst case time complexity of Euclid GCD algorithm. Log n plus log m is the total number of function calls or depth of recursion. Okay, so each function call required constant time. The total cost is log n plus log m, but log n is the leading. Log n is the leading. So the worst case time complexity, if n and m two consecutive Fibonacci numbers, okay, so then Euclid GCD algorithm behaves worst case. Okay, so worst case time complexity of worst case, or you can say average case as well. Worst case, average case time complexity of the above Euclid GCD algorithm. Okay, Euclid GCD algorithm is order of log n. Okay, so order of log n is the worst case time complexity. The Euclid GCD algorithm behaves worst case if n and m are consecutive numbers. If n and m are not consecutive numbers, if n and m are not consecutive Fibonacci numbers, sorry, n and m are consecutive Fibonacci numbers, Euclid GCD algorithm required more function calls. If not consecutive Fibonacci numbers, then Euclid GCD algorithm runs much faster. Okay, so it's a faster algorithm. See, if n and m consecutive numbers, what happening? N modulus of m is slightly bigger than half of n. Okay, almost close to n by 2. If n modulus of m, okay, more than half, right? So n is 45 and m is 34, modulus is 21. So 21 is slightly, okay, slightly less than, okay, so close to n by 2. slightly less than n by 2 means almost close to n by 2. Okay, if n modulus of m is slightly less than n by 2, little lesser than n by 2, okay, so close to n by 2 it becomes. So if by chance n and m not consecutive Fibonacci numbers, n modulus of m is become too small, n modulus of m become too small compared to n by 2. Okay, so if n and m consecutive numbers, n modulus of m is becoming close to n by 2. In that case, worst case time complexity is become log n. Okay, so this is one standard interview question also. So how many recursive calls made by the function? Number of recursive call made by the function more than n is not correct. Okay, and log n is not correct. Okay, root n is also not correct. Okay, the number of function calls are close to log n, asymptotically equal to log n. Okay, so got it? So this is the analysis for the Euclid GCD algorithm. It is one standard algorithm for interviews also, right?